is Generalized Linear Models with examples in R, and we're on question 4.7, so we're in chapter 4. Okay, so we, in the previous couple of questions, we have been looking at this probability distribution, the exponential probability distribution, and to this point, we have just been considering the parameter mu and doing things with mu, like finding the log likelihood and estimators, etc. And now we want to parameterize mu. This is what generalized linear models do, or linear models in general. We're going to take the mean parameter here, mu, and do something with it so that we can further parameterize it into other parameters and variables that allows us to use these predictor variables to predict mu, or at least some function of mu. Okay, and here we're taking that the natural log of mu is this function right here, an intercept plus a slope times x. Okay, and so we're going to do some things that we've done in previous problems. But first, I want to do some background, and then we'll get into the answers here. Okay, so the first thing I want to do is to kind of explore this idea of making the natural log of mu equal this linear model. So in previous chapters, we would, if we were going to regress something, we would regress y on some function xb. Now, when y is normally distributed, then when we're regressing y on xb, we are also doing it is the same thing, and you'll just kind of have to follow along for the statement to make a lot of sense. But that's the same thing as regressing the mean of y, which is mu, on xb, and the extent to which y varies around that is often denoted by an epsilon term. Okay, but now we get into these models that are not assuming a normal distribution, and just simply parameterizing mu as x beta. This is capital beta to represent a lot of different coefficients. This conversion doesn't work well anyway. And so what we do instead is we take some function of mu and set that equal to x beta, okay? And the function that we use for mu is often called the link function, and you often see it denoted as g of mu, right? So this is a generic function, okay? Where in this example, we're going to use the natural log of mu. So in this example, the natural log of mu is our g function. It's our link function. Now, we can, going back just to the generic function here, we can make an equivalent expression if we take the inverse times, if we multiply both sides of this by the inverse, right? So if I multiply g of mu by its inverse, well, then I just get mu, and then on the other side I have the inverse function of the linear function. Okay, and so in this case, in the case that we're working with right now, the natural log of mu equals x beta. If I inverse both sides, well, the inverse function of the natural log is exponentiating it. Right, so if I take the exponentiation of the natural log of mu, I get back mu, and then the linear function becomes e to the x beta, or the exponential of x beta. Okay, so now I want to maybe expand a little bit on how this is different from the normal linear regression that we've explored in earlier chapters. Okay, so let's take that y is a normal variable, which is to say that after you account for whatever x and beta are accounting for, that epsilon is normally distributed with a mean of 0. Okay. Well, then in this case, what we get is that the expected value of y, which is to say, mu, right, is the expected value of the linear function plus epsilon. And so we can break that down into two expectation terms. Well, x and beta are constants, and so its expectation is just simply x beta. And the expectation of epsilon is 0 by definition, right? Because we're assuming that it's normally distributed with a mean of 0. Okay? And so with normal linear regression, we have that the expectation of y is x beta, all right? Which is also to say that y equals x beta plus epsilon. Okay. Now we can, we can put this normal linear regression into the form of an with a link function. Okay. And so here the link function is this I, which is to say the identity function, which just spits back whatever is inside there, right? So here, for normal linear regression, g of mu is I of mu, where I of mu equals mu, which is just the expectation of y, equals x beta. Again, this is for the normal linear regression case. But again, if we're not assuming a normal distribution, then we have to do something different. Now, one thing that we have done up until this point, is to transform y. Okay. Now, notice that is different than transforming mu, a parameter that's describing y. But we might transform y, so we might call that h of y equals something, right? And the hope is that by transforming y, we are, somehow making it more compatible with a normal distribution, or the assumptions of a normal distribution. But to transform y is very different than transforming a parameter of y, which is mu, right? So if we run a regression on the transformation of y, then that means that that our estimates from that analysis refer not to y, but to some transformation of y. Okay. Whereas if we are using a link function on the mean parameter, we can always easily get back to how x and beta refer to mu and therefore to y. Okay. So how do we actually put some rubber on the road here? Well, you might naively think that the thing that we need to do is to go back to, so what do I mean rubber on the road? So if we're trying to, get a log likelihood and all of the downstream things from the log likelihood, well, then maybe it's as simple as taking the expressions that we've already found in, questions 4.5 and 4.6 with the same probability distribution, and just simply substituting e to the xb everywhere we see mu. But this is going to turn out not to work. And the reason that this is going to turn out not to work is because when we are using x beta, we are assuming that every observation has its own unique mu value. Okay. Whereas previously we were just looking for some monolithic value for mu. Now we're saying that every observation has its own mu based on the x's, based on the predictor variables associated with that particular observation. Okay, and so just making the substitution does not work. Okay, so we have to account for the fact that every observation is going to be unique and it's going to have its own unique mu, right? Based on the fact that it has its own unique x's. It's the betas that are going to be consistent all the way through now. Okay. So to do this, we can go through some steps here, and these steps I don't really think are laid out in this book, and I kind of took inspiration and modified these from a book that is called Generalized Estimating Equations by, let me check the author here for you, by Harden and Hilby. So anyway, I don't think that this book talks about generalized estimating equations, but you know, it's a good book and maybe worth looking at. So, okay. So we'll go through step by step how to get the log likelihood here. Okay. So the first thing we need to do is to choose a distribution for the outcome, and we already have that. Okay, right there. And now we want to write the joint distribution for the data set. Okay. So again, that just means, you know, take every observation and you take the product. And so now we're going to convert the joint probability distribution into a likelihood. Okay. Well, that's just simply restating this, right? Where instead of making y contingent on mu, we make mu contingent on y. That's what the likelihood is. Okay. And now we allow each observation to have its own unique parameter or set of parameters here. Okay. So in this case, notice that all we've done is we've said that every observation has its own mu value, right? By adding this little subscript I, where I refers to a specific observation. Okay. And so now we take we can log this to get the log likelihood. Okay, and that's what's happening here. Okay. And now we will we need to select a link function well, okay, so we can read this, but I feel like it's a little bit you need an example to really understand what this means. But we need to parameterize parameterize all of this by selecting a link function that ensures that the distribution or that the parameter follows certain criteria here. Okay, and so here we need to make sure that mu is greater than or equal to 0. Okay, that's just you need to know something about the exponential distribution to, you know, have intuited that. But the exponential distribution is a positive probability distribution. It can't go below 0, and so that means that mu has to be above 0. Okay, and so that is why an appropriate, it is not the only possible link function, but that's why an appropriate link function then would be the natural log, right? Because, you know, you can't go below 0 with the natural log. And now with our link function, you know, being applied to our mu parameter, now we can replace anywhere with a log of mu with xi beta, or equivalently, we can take mu I and replace it with e to the x beta. Okay. And so we make these replacements to our expression for the log likelihood, and we go through and we come out with this right here. Okay. So you know, so these are some generic steps that you can use to, you know, to do this to any probability distribution. Okay. And so now with all that out of the way, now we actually get to the actual problems. Okay. So the first thing we want to do is to show that the score vector has the elements, you know, this and this. All right. So remember, the score vector is just simply the first derivative of the log likelihood, and now our log likelihood has two parameters here. I'm just nicely wrapping them up into big beta here, but that has beta naught and beta 1, an intercept and a slope. Okay. So you can do this in several ways, but I'm going to treat the parameters beta as a vector here. But, you know, you could parse these out and do each parameter individually. But I just thought it was interesting to do this way. Okay, so we're going to take the first derivative of the log likelihood, and this video is already getting long, so I'll just kind of let you work through the steps here. But the steps are all laid out. But, you know, if we treat beta and we treat xi as their own individual vectors, okay, and we get an xi for each different observation, right? Because you might have more than one predictor variable. We work all the way through, and we get this generic expression for the score function. Okay. Well, now for xi, we put in the values of the observation, and those are going to be 1. Okay. And 1 is because every observation is assumed to have the intercept, and that corresponds to the intercept. Oops. as well as the value of that predictor variable for that individual. So notice how the 1 corresponds to beta naught, the xi corresponds to beta 1. And so if we plug those in, this expression right here becomes this expression right here. And so first we run through with the 1, okay, and then we run through with the xi, and we get 2 expressions, right? Again, the first one being the partial derivative with respect to the intercept, and the second one with respect to the slope. And we see that these correspond to, you know, what we're meant to show. All right. So now we need to show the second derivatives of the log likelihoods contain these values right here, or I guess this value, and this value, and the cross term, this value. Okay. So once again, I'm treating this all as just one big vector. I just, you know, it's a little bit parsimonious. Oh, excuse me. And so we're going to take the second derivative of the log likelihood with respect to the beta vector, which again is just beta naught and beta 1. I'm just condensing it here. Okay. Well, that's the same thing as the derivative of the first derivative of the score function. Okay. So remember, what's our score function? Well, we have it right here. And I go through and I take the derivative, and all of the steps are laid out here. And you eventually get a generic expression for it right here. And then remember, every xi is really one xi, okay, like this. And so now I have a vector, and it's transpose vector, and that becomes a 2 by 2 matrix like this. And then we can just multiply, this guy right here into that matrix. And what we come out with is this right here. Okay? And so if we look at this right here, we see all the terms that we're meant to show are in there. Okay, so this right here is the second derivative for the intercept term. Okay, y over mu, right there. Okay, the second derivative is going to be, or I'm sorry, the derivative for the slope is this other diagonal term. Okay, so yx squared over mu, yx squared over mu, and then the cross term here is yx over mu, and that's what we get on the cross terms here. Okay, so again, I'm really just glossing over the details of how to derive this, but hopefully, the steps are there, and so hopefully you should be able to walk yourself through it, and just giving the outline here. Okay. Okay, so now using the above results, determine an expression for the standard error of beta 1, but we'll do beta 1 and beta naught because why not? We have we have all that information here. Okay, so first, let's work backwards from what we have here. Okay, or not from back towards what we have here. Okay, so the standard error of beta, remember, is just the square root of the variance of beta. Okay, well, what's the variance of beta? Well, the variance of beta is 1 over the information of for beta. Okay, so in other words, it's the inverse information matrix. Okay, or the expected information, I should specify. Well, what's the expected information? Well, it's the negative expectation of the of the second partial derivative with respect to beta. Okay, so right now what we have is just this thing in the brackets here, right? And so that's what this is right here. And so if we want to find the standard error, well, first we're going to have to get the information, the expected information of this. So what we had up here, we need to take the negative of this and the expectation of it. Okay, so that's what's going on right here. Okay, so again, we take the expectation and minus it. We get this as our information matrix, and then remember that the variance is the inverse of this. And so to invert it for a 2 by 2 matrix, you first find the determinant, which is the product of the diagonal minus the product of the off diagonal. Okay, so you see that right here, and then I flip the diagonals, right? So this n and this sum of x squareds flip places, and then I put a negative on the off diagonals. Okay, and then you just push through, and you get any number of final expressions for this depending on which one's convenient to use. Okay, so I took it all the way to here, but you might push this through the parentheses, or you could do any number of things. And then finally, the standard error is, well, it's the square root of the variance for beta. So now I just take one of my final expressions and I square root it, which is the same as taking it to the 1/2 power. And so, when you do that, so if I multiply this by this diagonal, right? So that becomes the variance. If I multiply this outside part times this diagonal, I get the variance for beta naught. And then if I take this times the other diagonal, I get the variance for beta 1. And these off-diagonal terms don't really, those are covariances, but they don't correspond. They don't have a corresponding standard error term, right? Because the standard errors, they refer just to the parameters, not the cross terms. Okay, so here you have the standard error for both coefficients. All right, and then finally, we need to define the Wald statistic for beta 1 equals 0. But again, just because we can, we'll also do beta naught is 0. So we actually have two null hypotheses, okay? And so we're also going to solve this in two different ways and get two different answers. Okay, so what do I mean? Okay, so first we're going to treat beta naught and beta 1 as being individual hypotheses. Okay, so we're just going to take the estimate for beta naught and for beta 1, put them into a Wald statistic, push through and find a final expression for them. But we might also want to know what is the probability of we might also want to assess these two null hypotheses jointly, right? And that's going to be a different, that's going to be a different expression. Okay, so let's start with beta naught here. So this is just a generic expression for beta naught. Okay, and so here our null hypothesis is 0. Okay. Really should find a better way to denote that, but this is my null hypothesis right here. Okay, and it's 0, so I can just get rid of it. And the variance for beta naught we already saw is it's this times that right there. Okay, so we push through, and we get this final expression right here. All right. Now, one thing to note is that in the past we might have, if we were working with mu, we might have a analytical expression for mu, and that would be in here. But here we're just saying, we would have had an expression for our estimator for mu, but here we just have we've just put beta in there, beta naught in there. Okay, now the reason is, and this question doesn't really have a good place to address this, but it's because way back up here, where we were looking for, let's see, maybe right here, when we got the score function, normally what we would do to find estimates for beta, for the betas, is we would take their respective score functions, set them equal to 0, and then solve for beta. Okay, we could find a way to change that mu into the linear model here. But typically in generalized linear models with non-normal distributions, there is no closed form analytical expression, and so you need to use some kind of numerical algorithm to find a solution. And so these are like maybe Newton-Raphson, or what is I think most commonly used is iterated least squares. But I'm not sure if this book covers that or not. When it does, we will cover it, but it's a little bit too involved to put into this video. So again, all of that to explain why in our Wald statistic we do not have an expression for beta hat. We're just putting in beta hat. Okay. And so now similarly for beta 1, we use that generic expression. We find the expression for the variance, which again is this times the other diagonal. Okay. and then we push through, push through, push through. Okay. And in both cases, we have that, the final expression, well, I mean, all of these expressions because they're equivalent, but they are distributed as a chi-square distribution with 1 degree of freedom. Now, if we wanted to check the joint distribution, well, then we might construct our Wald statistic like this, but now beta hat and beta naught, these are vectors now, okay, and so that's why they're bolded, and so too is the variance, right? The variance is a vector, so all this is vectors, and so in matrix notation or matrix operations, there's really no such thing, or I mean there is, but when we're thinking about dividing something by another thing, that's not really how we do it. What we do is we multiply things by the inverse thereof. Okay, so so if I'm going to square this top term, well, that's the same thing as multiplying it by itself. And the way that we do that is we take that term and multiply it by itself. Okay, and so to make sure that the vector that the vectors line up appropriately during the matrix multiplication, we transpose the first one. If you're not familiar with matrix multiplication, then I'm afraid that some of that's just going to go over your head. If you are, you understand what I'm saying here. And then we're going to represent dividing it by the variance. Well, remember what the variance is. It's 1 over the information matrix. Okay, and so if it's the inverse of the information matrix. Well, so if I'm going to divide by the inverse of something, that's just re-inversing it. Okay, and so now I just multiply by the information matrix. Well, now, so now for beta naught, for the null hypothesis here, we have that that's 0. So all of this condenses to this form right here. Okay, and so now we can represent this in maybe the full depiction of this. And then when you push through, when you do your matrix multiplications, starting over here on the right and pushing through and then incorporating everything, you get this final expression for the joint Wald statistic. And notice here that now the chi-square distribution has 2 degrees of freedom as opposed to 1. Okay, that was a very long video, and we'll stop there.